If you ask people to describe a black hole, they'll picture a terrifying vacuum cleaner roaming the universe to suck up everything in its path. In reality, a black hole follows the same laws of gravity as everything else. If you replaced our sun with a black hole of the exact same mass, the Earth wouldn't fall in. Our orbit wouldn't change at all. The defining trait here is density. A stellar black hole can pack the mass of 20 suns into a space only 10 miles across. To truly understand these objects, we have to look past the sci-fi tropes and see them as physical structures defined by two extremes: immense weight and microscopic scale. These objects are born when a massive star runs out of fuel and collapses under its own crushing weight. Imagine gravity as a current. Space-time itself curves and flows like a river toward a dark depression. Eventually, it hits a point of no return, the event horizon, becoming a vertical waterfall. The current is so strong, escaping requires traveling faster than light. If you fall down this waterfall, gravity at your feet becomes significantly stronger than at your head, resulting in a violent vertical stretching called spaghettification. Once matter crosses that event horizon, it leaves the familiar physics of our universe behind. At this point, you might wonder what happens to all the complex matter of that crushed star once it disappears into the dark. As it turns out, the black hole deletes every complex trait the star once had. It can be described entirely by just three properties: its mass, its spin, and its electric charge. This makes them incredibly simple. Any two black holes with the same mass, spin, and charge are completely identical to each other. Einstein's theories suggest that this lack of distinguishing features makes black holes behave less like stars and more like fundamental subatomic particles. They are essentially quantum particles, only scaled up to the size of a city. Stephen Hawking expanded on this by showing that black holes must interact with the microscopic quantum vacuum of space. At the subatomic level, the vacuum of space is alive. Tiny particle pairs spontaneously appear, immediately colliding and vanishing. Right at the event horizon, these pairs separate. One is pulled inside, while its partner escapes, stealing a tiny fraction of the black hole's energy. This constant quantum leaking, or Hawking radiation, means black holes aren't permanent. They glow softly as they slowly, inevitably shrink. Over trillions of years, this evaporation process will cause even the largest black holes to disappear entirely. Until that happens, they act as critical gravitational anchors, shaping and holding together the galaxies we live in. Sometimes two of these objects will orbit each other, spinning faster and faster in the dark until they violently merge. This collision acts like a mallet striking a drum, sending ripples vibrating through the fabric of space-time itself. On Earth, we use massive instruments like LIGO to listen to these invisible ripples, allowing us to reconstruct the size and shape of the objects that made them. These massive, vibrating particles orchestrate the very shape of the cosmos, glowing softly across the eons as they anchor our universe together.